Hello, everyone. Thank you, Jeff, for the introduction. My name is Maria Krivova, and I'm a PhD student at Oregon State University School of Civil and Construction Engineering. In this work, I'm trying to combine photogrammetric and GIS skills to achieve a result that can be scientifically valuable. In June 2017, a large field experiment was conducted where the Connecticut River discharges into the Long Island Sound. The cross of the tidal currents is interesting oceanographically, and the location was selected primarily because of its complicated and shifting physical properties, where the remote sensing method should help study these frontal structures and qualify them. The relationship between the tidal currents and the river discharges has been previously observed and recorded there using traditional acoustic instruments. The front line, the line which divides river water, and seawater, is shown in the video. A lot of short videos were taken in this area, including tracking videos and static ones. It should be noted that the area depicted on the video doesn't contain any land surface. It only contains the unstable water surface. So only camera parameters and GPS positioning have been used for the rectification. The rate of the video is 30 frames per second, so 5-minute video has about 10,000 images. Technically, the developed algorithm can process each of them. However, in this case, we actually don't need to do this. And after some analysis, the 5-second time period has been chosen as the most reasonable one. All chosen images then were rectified to the UTM projection. The map on the left shows the position of the georeferenced image. After georeferencing, the maximum likelihood classification has been applied to extract the front line. A lot of little extracted front line polygons are depicted by the white color in the picture on the right. After the classification, I generated centroids of the front line polygons, which are depicted by green color here, green points here. After that, some outliers like sunshine reflection or watercrafts have been removed, and then Python median filter has been applied to adjust centroids of the extracted frontline class. So you can see a blue line here after the filtering. Even though this line, which represents the front between fresh and salt water, looks pretty good, it's still wiggled. So here on the zoomed image, I applied more adjustment to smooth the line, because without this, we will have some cross-correlation errors in future due to noise of these wiggles. So this yellow line is smooth line. I will say more about the cross-correlation in the next few minutes. Also, you can see the red line on the image, and this is a especially important feature. Let's talk about this. One of the goals of this research was to estimate the frontline propagation speed and the amplitude fluctuation. In order to do it, we need to generate a fit line, which is obviously not straight. So I used Python low-pass filtering to create this polynomial line, which is represented by red color here. After the smooth and yellow and polynomial red lines have been created, we need to begin the preparation of our data for the cross-correlation. As we know, the number of points of the cross-correlation of two data sets have to be the same. This is why the equal number of points have been generated on the smooth line for every image. As I said before, we need to estimate the amplitudes of the front line, and near tool fits perfectly for this purpose. So I use points in this line to run this tool. Now we're almost ready to perform the cross-correlation, but we don't know which amplitudes are positive and which ones have a negative sign. So to change the sign for the amplitudes, which are delta y, here at the attribute table, I created two polygons, let's say A and B. And every point which is in polygon A will have a positive sign, and points are included in polygon B will be negative. And voila, our amplitudes have a sign. The tables then were converted to Excel and were ready for the future analysis. This image shows the cross-correlation of one pair of the image with 5 seconds of difference between these front lines. Let's say frontline 1 and frontline B, or frontline 1 and frontline 2. One of the output of the cross-correlation measurements is lag. Knowing the lag, which is the distance of the waves shifting, and the time difference, which is 5 seconds here, we divide distance by time and get the speed. In our case, is the propagation speed. Here at the left graph, we can see the average cross-correlation coefficient, which is calculated using all pairs of the video. On the right picture, we can see how amplitudes change through the video. The novelty of this method is that it gives a very precise, robust, and visually elegant identification of the front lines. The GIS approach allows users to visually, using the map, estimate the process, as compared with the previous research where mostly mathematical estimation has been conducted and where probably a coherent projected representation has been lacking. So the final map shows a selected frontline propagation with the 10-second lag. So it was impossible to put all 50 frontline here. I show only 5. Also, this approach can be applied for the processing and analysis not only water surfaces, but also other unstable surfaces like forest fires, volcanic movements, or hurricane propagation. And this was my presentation. Thank you.